right, so welcome in, and today we're going to go ahead and do a review on free body diagrams or forced body diagrams and Newton's third law. Now, you can go ahead and pause this video and write down these scenarios, and you should do these images and FBDs basically off memory. So don't look at your notes, but go ahead and draw these out. And once you're ready, you can move on. There's a total of 11 of these scenarios. So here's 1 through 5, and here's 6 through 11. So pause the video, and you don't have to write the scenarios, but just go ahead and draw each free body diagram one at a time. Okay, so now let's go ahead and look at some of these scenarios. All right, number 1, a book is at rest on a tabletop. So the book is on a surface, and that's where you see that little red line. And once you have a surface available, you have F normal, or normal force. F gravity is always present, and these two forces are balanced. They're equal to each other. The object is not moving one way or the other. Number 2, a physics project is suspended from the ceiling by 2 ropes. Now we no longer have a surface, so we don't have F normal. Instead, the weight is being supported by 2 ropes, 2 F tensions. Each one is called, or the first one is called FT1 for force tension from the first rope. And the second one is FT2, force tension from the second rope. And these two added up to each other will equal our FG. So they balance out with the FG, or force due to gravity. Remember that each rope's string, sling, or wire, or chain, whatever it may be, requires its own separate vector. So had this been supported by 3 ropes, it would have been 3 vectors of Ft, each being a little smaller, 1/3 the original size of Fg. An egg is free falling from a nest in a tree. Neglect air resistance. So when an object is in the air, the only thing that's affecting it, if we neglect air resistance, is gravity. We have no other control over it. So the only force is force of gravity. Number 4, a flying squirrel is gliding, so it's not doing any wing flaps, which means there's no force applied. And it's going from a tree to the ground. It's in midair at constant velocity. So with constant velocity, we have the force gravity in the air, and we have F air resistance that is balancing out with F gravity. Again, since this is in the air, it is not making contact with the surface. It is in the air, and you don't have F normal. Instead, you have F air, or F drag. Keep in mind that F air and F drag are both the same thing. Number 5, we have a rightward force is applied to a book in order to move it across the desk with a rightward acceleration. We're going to consider frictional forces. We're neglecting air resistance. Now, when you have 2 objects making contact with the surface, you obviously have F normal, or normal force. That's indicated with the perpendicular that is going up. It is a rightward acceleration, which is the key word for that problem, which means that our right arrow is going to be longer than our left arrow. So force applied vector is longer than the force friction on the left-hand side. Remember that friction is a contact force, and it's present when 2 surfaces, 2 hard surfaces, are making contact with each other. F gravity is always present, and F normal is perpendicular to the surface, not to the object. F gravity is straight down from the object, whereas F normal is perpendicular to the surface. Now let's compare this to number 6. Number 6 is pretty much the same exact scenario, except the only difference is that it moves across the desk with constant velocity. So when you have constant velocity, our picture changes a little bit. Now that means that constant velocity is 0 or no acceleration. Therefore, the force applied and force friction are balanced. When your forces are balanced, it means that the net force is equal to 0 newtons. Think about the example that we did with the lemonade stand with the profit and the expenses. In order to be balanced, you need to break even. So this is what's happening here with these forces. They're breaking even. The net force is 0, which means it's not accelerating one way or the other. It's moving at constant velocity. One of the biggest misunderstandings about constant velocity is that students think that it's not moving. Again, constant velocity happens anytime, such as when you put your car on cruise control. Let's say you're driving down the highway and you put your car on cruise control at 60 miles per hour. You're going to go that 60 miles per hour for the duration of that trip for as long as you have cruise control on. You will not accelerate one way or the other, meaning that your speed will not change, increase or decrease, but it will remain the same, constant velocity throughout that moment. Mathematically, forces are balanced is written as EF is equal to 0 newtons. All right, number 7, we have a college student that rests a backpack upon his shoulder. This backpack is suspended by one strap from the shoulder. So now we only have one F tension. Again, there is no F normal because the object is not making perpendicular contact with the surface. So you have to keep that in mind. The weight of the object is supported by the F tension. There's only one strap, and therefore we have F tense is equal to F gravity. In an earlier picture, we saw one where it was supported by 2 ropes, and we had 2 smaller F tensions. So just keep in mind that each vector or each rope, sling, chain, and string or wire will require its own separate F tension vector. And number 8, as I mentioned earlier, the picture doesn't correctly show up. So number 8, it says a skydiver is descending with a constant velocity. Consider air resistance. So this is Fg is equal to F air. Fg is always pointed down, and F air or F drag, which are both the same thing, is equal in size, just in the upwards direction. So we have our Fg down arrow the same size as our F air or our F drag arrow going up. Number 9, we have a force that is applied to the right in order to drag a sled across a loosely packed snow with a rightward acceleration. So again, rightward acceleration or any kind of acceleration means that vector or that arrow needs to be longer in that side. It is making contact with the surface, so we have a red line to indicate that. And once you have a surface, you have your F normal or your normal force present. The loosely packed snow is causing friction. However, it's not enough to slow it down or in order to keep it going at a constant velocity. So the right side, the force applied, is much longer or greater than the force friction, and it is accelerating towards the right. Number 10, this is similar to a quiz question that you may have seen, and this will come up on quizzes and tests. And so take big notes on this. You have a football that is moving upwards towards its peak, meaning it's already in the air after having been kicked by the punter. Neglect air resistance. So remember that we've said in past that, when something's in the air, you no longer have control over it. You can't continue to apply force to it. So the FBDs, or force body diagrams, they depict the forces that are available and happening at that given moment. So the football is moving upwards towards its peak after having been already kicked. And this is not the moment of being kicked. This is being kicked or having been kicked. So F gravity is the only force that is present if we neglect air resistance. Now let's compare this to an alternate scenario. This one was a football moving upwards. The alternate scenario would be if you have a basketball passed to another player and that is thrown horizontally. As you notice, there is no difference between the pictures because you don't have to indicate the movement as horizontal or vertical since the object is in the air. When an object is in the air, the only force acting on it is force gravity, and they specifically told us that we're neglecting air resistance in this problem. Now we're going to go ahead and see another alternate scenario, and this was the quiz question that you may have seen, or a version of this. And it's a frisbee thrown in the air and is about to be caught by a dog. Do not neglect air resistance. And this is our free body diagram. So again, the frisbee is already thrown. You are no longer applying a force. That is why you have no force friction or force applied. It's also in the air, and friction doesn't occur in the air. The only thing that occurs in the air is force drag or force air. So we have force gravity, which is present at all times, and we have F air or F drag that is slowing down this object. Again, it's not being caught by the dog yet, so there's no force by the dog in order to stop this, and you have thrown this frisbee, so there's no more additional force to keep it going. This is already in motion, and the only two forces present are force of gravity and the F drag or F air resistance. All right, and we've seen this in a scenario before with the car coasting to the right and slowing down. Again, you don't always need a vector in order to show movement. The vectors are for the forces present in that given moment. This is a force body diagram that we're drawing, and you're drawing the forces that are present in that given situation. So remember that the whole concept of FBDs is to show what is happening right now and not what might have happened to the object before. We don't care about how the car achieved its velocity. We don't care about the fact that someone threw the frisbee or that the punter kicked the ball. Those were forces applied before. Our problems stated when the ball is in the air, when the object is in the air, when the frisbee is thrown, or in this case, as a car is coasting to the right. Coasting means that you're no longer applying gas and there's no foot on the throttle. Therefore, you are no longer applying a force to keep the car moving. The car is moving from a previous force. The only thing that is causing this car to slow down is force friction. Now, the car is going to the right, and friction is in the opposite direction of motion. So the force friction is on the left-hand side. All right, let's go ahead and clear up some misconceptions about forces in general and different things. Now, as I've said before, I'd rather you guys not write this down because this will be available on Canvas and you guys can come back to it. I'd much rather you guys be able to listen and grasp this rather than try to write these things down. So just take a moment, just listen to it, understand what is happening. You can always come back and write this. We've talked about net forces a lot. Net force isn't an actual force. It's the sum of all your forces. If you notice in any of your FBDs, we never drew a net force. We drew force tension, we drew force drag, we drew force applied, force gravity, force normal, but we never labeled one as net force. And that is because net force isn't an actual force. It's the sum of all your forces. Let's take this as an example of your grades. You have your final semester grade. While you see your final semester grade, that isn't an actual grade in the sense that you never came one day to school, took one assessment to make that grade for the whole semester. Your semester grade was the sum of all your other grades, the assessments that you had leading up to it, the homeworks, the quizzes, the tests, and all of those added up together eventually gave you your semester grade. So that's the difference between the two when we talk about a net force being the sum of the forces and not being an actual force. Net force is also different than normal force. I know they'll both start with N, but remember that net force is referred to as the capital F or EF, epsilon F, and normal force is simply Fn. Fn is equal to apparent weight. We've said that weight depends on gravity and weight can change. The cheesy way that I've taught you guys this before is if someone says that, I like to lose weight without having to change my diet, without having to do any exercise, the easiest way to lose weight is to go to a different planet. So weight depends on gravity. If you go to a different planet, we got much less gravity, you're going to have much less weight. So weight can change, but mass does not. The other cheesy way to remember this is like the infomercials where they say, but wait, there's more. Call now within the next 5 minutes. Nobody says, but mass, there's more. So it's, but wait, there's more. So if you can have more weight, you can have less weight. The change in weight means that it fluctuates. So remember the little infomercials when it says, but wait, there's more. Weight can change, mass does not. If you ever need to find the weight, it's equation number 9, and its weight is equal to Fg is equal to mass times gravity of the planet. If the problem does not say what planet it is, we're always going to assume that it's on planet Earth with the acceleration due to gravity is negative 9.8 meters per second squared. If, however, it's on a different planet, we will provide you with that AG. Make sure that you use the appropriate units. Weight is a force, therefore the units is in newtons. The unit for mass is kilograms. I know here in the States we're used to using pounds, but keep in mind that these are not physics units. And for physics problems, you're going to need to use the correct units. So if weight is a force, any force always has the unit of newtons. The unit of mass is kilograms. I've taught this from the beginning of the year, is make sure that you're paying attention to your units. Don't forget to convert. If mass is given to you in grams, and you will see this in tests and quizzes where your problem states the mass in grams, you have to convert it to kilograms before proceeding. Force causes acceleration. Remember, the equation is F equals ma, where the A stands for acceleration. Its force is equal to mass times acceleration, not movement times acceleration or mass times movement. So its force time is equal to mass times acceleration. It's the acceleration that causes an object in order to speed up, slow down, move from rest, stop motion, and or change direction. A force doesn't always cause movement. Take your book or take your Chromebook, for example, right now. You could press down on it and you can apply a force, but by doing so, you're not moving it. You could also take both hands and apply force from left-hand side as well as the right-hand side towards the Chromebook, and you're not going to cause it to move. So a force doesn't always necessarily mean that it can cause movement. And the other thing that I've touched on is that not every FBD may have a force vector in the direction of movement. Think about the car coasting to the right example. There was no arrow to the right. Think about the basketball that was thrown horizontally. There was no vectors for that one. Think about the punter that kicked the ball. There was no force vectors being applied for that one. The only thing that we had was F gravity. So it can be moving. It doesn't need to have a force applied in order to keep moving in that scenario. And as I've said earlier, constant velocity means that there is zero or no acceleration. Again, don't get this confused. I think that constant velocity means you're not moving. You're moving at a constant speed. So go back to the cruise control example, 60 miles per hour. You are going to continue to go 60 miles per hour, and that is not having any kind of acceleration. Now, I know the word normal, or when we say force normal, it sounds a little odd, but in physics term, normal literally means perpendicular. So when we say normal force or Fn, we are literally saying that it's the perpendicular force that is to the surface. And normal force is only present when you have a surface available and the object is making contact with that surface. Normal force is a contact force, and it's the support force that is exerted upon the object that is contact with another object. So let's take your Chromebook that is resting on the desk right now. The surface is exerting an upward force, that surface being your desk in front of you, is exerting an upward force onto your Chromebook in order to support the weight of the Chromebook. And the weight of the Chromebook is equal to the Fg, which is mass times gravity. So the force of gravity on Earth is equal to your weight. However, Fg is pointed down, and that is negative. And you can't have negative weight. That's why the Fn, or a normal force that is pointed up, is equal to our object's weight. And finally, remember that force friction is also a contact force, and it's only present when two objects make contact with each other and two surfaces touch. There is no force friction when the object is in the air. That's called F drag or F air resistance. So hopefully these little misconceptions can be cleared up now. All right, let's look at this picture. From this picture, can you really tell if it's moving or if it's at rest? The truth is, you can look at it and we won't ever know, because Not that because we don't know what the left-hand vector is. I've already said that it can be either force friction or force applied. It could be either one of those. But this is an object that is balanced. And remember, when we say balanced forces, it means that the net force is equal to 0 newtons. So forces don't always cause movement. Forces cause acceleration. And an object with balanced force could be at rest or could be at moving with constant velocity. So when we look at this picture without knowing the word problem, we don't know which is which. Again, this could go back to the object, the force applied is equal to the force friction. And that is the same amount that is balancing each other out. So it's moving at constant velocity. Or it could be like the example of you pushing your Chromebook from the left-hand side to the right-hand side with equal forces in opposite direction that cause the object to remain stationary, even though you're applying a force from both ends. So we don't know what's happening unless we know the word problem. The only time that we are aware of that it is actually truly moving is if we had one of these vectors, one of these arrows, longer on one side than the other. That's when we know we have a definite acceleration, and that's when we know we have motion. All right, so let's go ahead and do a problem. This is a similar problem that you saw on your quiz. Now, this one's a little bit harder, so we're going to go ahead and solve this out. So let's write down the gist of the problem. You got a girl who's pulling on a 40 kg wagon. Again, you have to write it all word for word. Just let's get the main information, and this will be available later on as well. You have a girl that pulls on a 40 kg wagon with a force of 300 newtons. The wagon's wheels have a force of friction on them, which is a magnitude of 60 newtons. What's the acceleration of the wagon? So we are looking at the acceleration. Now, the first thing that you do is we're going to go ahead and draw our FBDs. So I'm going to give you guys a few seconds to draw the FBD for this scenario. All right, let's look at how your FBD compares to the FBD here. So the wagon has 40 kg. We're going to put the mass inside. There's a surface. FG is always present. When you have FG, you also have FN. There's force applied to the right. Now, the problem never stated that it went to the right, but like I've said before, if it doesn't say which way it's moving, consider it to the right so that friction's to the left and it counts against you. So force applied has a longer vector to the right-hand side with a value of 300 newtons, and the force friction is to the left with the smaller size, and it is negative 60 newtons. Now pay attention to the problem. The problem said it had a magnitude of 60 newtons. The problem will never tell you that it's negative. It's your job to recognize that it's going in the opposite direction and it's counting against you, like the expenses in our lemonade stand example. So it's negative 60 as far as the force friction is concerned. I don't have FG or FN, but at the same token, I don't need to have those values because I'm looking at the acceleration of the wagon in a horizontal point. So my job is to basically only focus on the X component or the horizontal component of this. So let's go ahead and do our steps, which is list our knowns and unknowns. Our unknown is acceleration. The unit for that is meters per second squared. The mass is 40. And we're going to go ahead and list what the net force in the X direction is made up of. So when we look at our diagram over here, we see that in the X component, we have two forces, force friction and force applied. The sum of those two forces make up our net force in the X direction. So EFX is equal to force friction plus force applied. we can go ahead and substitute our values, which is -60 for FF, or force friction, plus the 300 from force applied. The two of those added together gives us the sum of 240 newtons. That's the net force in the x direction. Now, we're not done just yet, because the question asked us to find the acceleration of the wagon and not simply the net force that is being applied to the wagon. This is just a clue or a puzzle piece that we're going to have to use. Okay, remember that our equation number 7, F equals ma, relates to this directional purpose as well. So now it's the F of x, meaning the force applied in the x, is equal to mass times acceleration in the x component. Again, this is where we go back to, if you're dealing with x, it's max. If you're dealing with y, it's may. So we're only dealing with the x scenario here, so it's Fx is equal to max. Net force we just found was 240, so we substitute that for that. Our mass we knew from the problem was 40, so 240 is equal to 40 times our acceleration in the x direction. So 240 is equal to 40 times a. The 40 is being multiplied by a, and in order to isolate a, we're going to have to divide by 40. So what you do to one side, do to the other. 240 divided by 40 gives us our acceleration in the x direction as 60 meters per second squared. So if you remember from your quiz, this was a similar exact scenario, just with different numbers. All right, now that we've taken care of the review session with Newton's FBDs, Newton's second law, let's go ahead and move on to Newton's third law. Now, the key word here is that there's force pairs. So make sure that you put a star there. Make sure that you are aware that Newton's third law deals with force pairs, and a pair means two. So Isaac Newton said that all forces occur in pairs, and these two forces are equal in magnitude and opposite in direction. We're going to go ahead and break this down, and we see what they refer to. Equal in magnitude means equal in numerical value. So again, magnitude, just a number value. The forces occur in pairs. That means they come in twos, and the two forces are equal in magnitude and opposite in direction. Have you ever stubbed your toe? Have you ever noticed how painful it is? Okay, so let's break that down from physics standpoint. What hit what, right? Did your foot hit the table, or did the table hit your foot? Did the table just basically reach out and make sure that it tripped you or hit your toe? No. So you both made contact. So it's not like your foot hit the table first and then the table hit back. And then how was the table able to apply so much force when it's not moving? So this is where Newton's third law comes in, and it gives us the explanation for this. One of the examples that they use for Newton's third law is also when a baseball makes contact with a bat. Look at the ball, look at the shape of it. There's going to be an equal opposite force. So whatever the baseball feels, so does the baseball bat, just like your toe and just like the table. You both feel the same exact amount of force, just in opposite direction. One of you may move, the other one may not. Now, we got to neglect the swing or the follow through, and we're thinking about this exact moment when this contact is being made. Some more prime examples are the action reactions from the following images. When the air goes out of a balloon, whichever way the air goes, the balloon goes the opposite way. When you have, well, you won't ever have a cannon on wheels, but for illustration purposes, you do. If the cannon shoots, the recoil is going to cause it to go backward, and the cannon itself will go ahead and go to the right. Another one is with a hammer and nail. If you think about it, the nail is stationary, and the hammer is coming down, accelerating, and has a velocity that's coming down, makes contact with the nail, and the hammer swings kind of back. So you get it bounce back. It went from completely picking up speed to all of a sudden not only stopping but changing direction because it felt an equal and opposite force from the nail. So all of these things are the same thing as stubbing your toe. All right, so Newton's third law in 3 bullet points. The forces come in pairs are essentially, these are the 3 things that make it happen, and they all have to happen. They need to be equal in value, equal in numerical value. They need to be in opposite direction, and they need to occur simultaneously. It's not like one thing happened and then the other happened. Again, go back to stubbing your toe. It's simultaneous. So equal in numerical value, opposite in direction, and simultaneous. Now, you've probably heard of Newton's third law in previous science classes, and they break it down and they simply that it's the action-reaction, but that's in its most simplest term, and it gives you a lot of misconceptions. It's really the action-reaction force pairs. It's the force pairs that we're concerned with. So for every action force, there's an equal in size and value and opposite in direction reaction force. So it's not just an action-reaction, it's an action-reaction force pair. Again, pairs comes in twos, and there's always 2 forces involved. It's the action-reaction force pairs. Now, let's see what some of those misconceptions. When you simply refer to as action-reaction, it might be that somebody thinks that action happens first, then the reaction occurs. That's the second misconception. If you think about the word action, there's a lot of actions that happen, but we're only concerned about actions that are forces. So it's action-reaction force pairs. So just keep that in mind. You go about doing a bunch of different actions throughout your day, but it doesn't mean that Newton's third law is occurring. So remember, for Newton's third law to occur, it needs to be equal in number, opposite in direction, and simultaneous, and the forces obviously need to come in pairs. So now let's break this down. The original example of stubbing your toe. Going forward, we're going to go ahead and have a lot of subscripts, such as FA on B and FB on A. And here's how you read this. The FA on B means that the force of object A onto object B. So object A is your foot or your toe, and object B is the table. So FA on B means that it's the force applied by your toe onto the table. The negative FB on A means that this is the force applied by the table, the second object, onto your toe, the first object. The negative indicates that force occurred in the opposite direction, but the value of F is still equal. And these forces were applied at the same time. So if you look at your foot or your toe, it's the one on the left, and it has a rightward motion. So that's positive. When it makes contact with the object B, the opposite force that it feels is in the left-hand side. So it's going to be going towards the left from that object. So that's the negative FB on A. We might refer to as F1 on 2, F2 on 1, or we might give them names, or we may have letters. But they essentially mean the same thing. Force of the first object onto the second, and the force of the second onto the first. This basically says the same exact thing, just without the picture. So force FA on FB means that it's the force from object 1 onto object 2, and FB on A means that it's the force from object 2 on object 1 in the opposite direction. That's where that negative comes in. If you look at the font sizes, the F is exactly the same, so the forces are the same numerical value. All right, here's a little thinking time. Is this Newton's third law, basically? Is this a force pair? Are FG and FN a Newton's third law force pair? What do you think? So the correct answer to this is actually no, because the 2 forces act on the same object. So if you haven't already wrote this down, make sure that you put a star and say that the 2 forces need to act on different objects. Okay, it goes back to the stubbing your toe. The toe and the foot is one object. The table is a second different object. So it needs to occur on different objects, not the same one. Fg, the force of gravity in this scenario, is the force of gravity by planet Earth pulling it down, and the Fn is the weight that is supported by the surface. So those are acting on the same object, which in this case happens to be the individual. The caption here, again, says the same thing in the past 3 slides, which is FA on B simply means from object 1 into object 2. FB on A means from object 2 on object 1. What we were just seeing here is the pictures that are considered to be examples of it. So when we look at the action of the man, he exerts force onto the ground, and he can move forward, and he also pushes onto the rock, the red arrow, but the reaction is the rock exerts force on man. Now, I'm not a big fan of this, so let's go ahead and do a different visual. We've all heard of and seen people do push-ups, right? So think about when you're doing a push-up. What's happening when you actually do a push-up? Are you really pushing up, or are you pushing down? Well, if you think about it, you're facing down, the ground is down, and you're pushing against ground. So really, you push down, but you push yourself up. As a result, you get Newton's third law, equal and opposite reactions. So by pushing down on the ground, the ground pushes up and you move up. If you want to think about truly pushing up, it would be like a toddler on its back and pushing into the air. If you did that, nothing would happen, because if you push into the air, pushing upwards, you're not making contact with any surface, and you're not going to receive an opposite reaction, equal force in the opposite direction. So you're not going to have any kind of movement. But when you do that onto the ground, you push down, and the reaction is that the ground pushes up and you move up. So that's a much better example. Let's pretend these individuals we have individuals who are on wheels, skateboards in this case. The forces that you see, the vectors, are forces. The green arrows are the original forces that they apply, and the blue arrows are the forces, excuse me, are the forces that they receive from each other. So 2 different objects are feeling the same amount of force. Person A applies a force the same amount as person B, and they both go backwards. If you look at person A in the bottom left, the blue vector is the force. It would be considered FB on FA. FB on object A. And if you look at the individual on the right on B, the vector for them is the FA on B, because originally that force was applied from individual A onto that individual B. Thinking about individuals on wheels will make a little bit more sense, probably easier, but the push-up example is a great one if you're ever in doubt. If the mass of the 2 objects are the same, both objects will accelerate at the same rate. So let's break this down. You have 2 individuals, same exact mass. If they apply the same amount of force, which they do, their acceleration is equal to each other as well, which means that they cover the same amount of distance, they travel the same amount of distance. The force pairs on both objects are still the same. Those vectors that you see are the force pairs. So the force A on B is equal to the negative FB on A. Force is still the same. What happens if, however, you have a difference in mass? Let's say one of the individuals has more mass. In this case, the individual A. The lighter person with less mass, object B, will now accelerate at a much faster rate compared to the heavier person with more mass in object A. Object B will move greater distance than object A. Think about the nail and the hammer, or the baseball and the bat. The lighter object will move a greater distance than the heavier object. Think about your toe and the table. You can kick this, I don't recommend it, but the next time it happens, you can look at the table and it will not move, but your toe did, meaning that it actually bounced back. However, the force pairs is still the same. They experience the same exact value. Now, this might be a little too many words, so let's just break it down with numbers in the equation. Let's say a force of 100 Newton is applied. That's your action force. We know that the reaction force would also be 100, but a negative version of it, so it's a negative 100. Let's say that the two objects that are in place, the first one only has a mass of 5 kg, the second one has a mass of 25 kg. If we look at the equation on the bottom left-hand side, we see that the object A, with the less mass, needs to have a much greater acceleration and will experience a much greater acceleration in order to have the same amount of force when you have the heavier object with the greater mass, object B, experiences a lot less acceleration. So these two are indirectly proportionate, meaning that as less mass is going to have more acceleration, and more mass is going to have less acceleration if we're talking about applying the same force. Let's look at the right-hand side now with those plugged in. Our F values are the same exact size, same exact value of 100. If mass of object A was 5, in order for us to be at 100, object A would accelerate at 20 meters per second, greater acceleration. When we compare that to object B, it's still 100 for the force, but it's in the opposite direction, so it's a negative 100. The mass is 25 because mass can't ever be negative. The acceleration numerically is 4 meters per second squared, but the direction is left in the opposite direction, so it's 25 times negative 4, which gives us a negative 100. So again, these are indirectly proportionate, meaning that if force is the same, the mass and acceleration affect each other inversely. So if you have greater acceleration, you're going to have less mass. If you have more mass, you're going to have less acceleration. And an easy way to think about this, well, we've had plenty of examples, but think about, when cars may collide or something like that, is if we've got this over here, a tiny car with a bigger car, if they were to accidentally become a forced pair, they're going to feel the same exact force. However, think about which one will feel the greater jolt. Smaller object will have greater acceleration in the opposite direction, whereas the heavier object will experience a smaller acceleration. Or think of it as when you're driving and the bug hits the windshield. Technically, the windshield and the bug felt the exact same force, but only one of them, survived. All right, going back to this, doesn't mean that you're always going to have movement. So if you stub your toe, object A, onto object B, obviously object A, your foot, your toe will bounce back. But however, the table will stay in the same position. So just because there's always acceleration involved doesn't mean that you're going to have some kind of movement. Again, it goes back to pushing down on the ground. You can push down all you want. The ground's not going to move. You will. So if the mass is greater for one object, much greater than the other, then it's not going to be affecting or change motion. But the force is still the same. All right, we are reaching the last two slides. And the big takeaway is that third law on the right-hand side, action pairs do not cancel out, okay? Because they're on different objects. So this is not an FGFN thing where you say forces are balanced. These are occurring on two different objects. As we see the volleyball player on the right, the girl is applying a force onto the ball with her wrist or arms, and the ball is also experiencing or applying a force onto her as well. So she's going to feel that hit later. And if it was, different objects and so on, it's contact. And it's the same thing with any kind of sport. Let's take football, for example. Running backs, unless the running back is truly gifted and very talented and once in a lifetime exception, running backs do not get selected very high in the draft because they're considered to have high mileage on them. Because if you think about it, a running back has been getting hit pretty much on almost every play, even sometimes when they don't have the ball. So they take that hit and they feel that force. Anytime contact is made, they're going to feel it. And this is why running backs are taken usually later in the draft, and they have a certain age limit, unlike most other positions. So it's kind of like, it eventually takes a toll on you, and it's Newton's third law that is occurring. Now, on the object on the left, two individuals are applying forces onto the same object. They're canceling out. So that's not Newton's third law. We've talked about the baseball example. I know it's hard to believe, but we're neglecting the follow through. So imagine at the moment of contact, the baseball forces bat to go backwards in the left-hand side, but it's very small, less mass. So it's not going to cause that much of a direction change. However, the bat is much heavier than the ball, which is going to cause the reaction of the bat forcing the ball to the opposite direction. Again, we're neglecting follow through and looking at the moment of contact. If you have an astronaut in the air, in space, and they push away on a small rock, or they throw a rock, the rock has a much smaller mass. So that should give you an idea as of which one will move further. Will the rock move further, or the astronaut move further? Well, it depends on their acceleration. And we said that less mass will give us more acceleration. So the rock will move further, accelerate faster compared to the heavier astronaut. All right, and finally, this is it. Again, remember to recap, equal in magnitude, opposite in direction, and they occurred simultaneously. And those two right there are the typical examples or pictures you may see in a question. So equal in magnitude, numerical value, opposite in direction, and simultaneous, they happen at the same time. All right, thank you very much. You guys have a great day, and see you next time.